All right, welcome back, my friends, to me figuring out the meta language, the Metta Type Talk, logic, relational, multiparadigm, AGI language. Okay, so let's go here to my setup, and then I can show you my recent achievement that is called meta mode el metamode.el. You can also find this on GitHub, meta mode, although this is very very early stuff. So the meta mode at the moment is a file that defines a mode in emacs, and it makes an interactive evaluator, inferior meta, and I'll just show you this in action. So I'm gonna evaluate this file. Iflet is a obsolete macro, alright. And then I have here a meta file. So now it will become meta. I get this sly because I inherit from Lisp mode at the moment. Now we can just ignore this. And I can actually, so I say run meta inferior, run a inferior meta, makes a process, a meta process, and now I evaluate, no, I type meta code, text increase, make it big. So this is meta code, and then I evaluate with single key, just the way that I usually evaluate lispy. Version and control. So that is some functional programming things. Basic recursion. A natural way to represent repetitive computation in meta is recursion, like in traditional functional languages, especially for processing recursive data structures. Let us consider a very basic recursive function which calculates the number of elements in a list. Okay, I'm gonna type this out. So length with like sort of the empty list, which we define sort of in an ad hoc way here right now, 0. Okay, then length, and then we say sort of colon as kind of like a cons length of this, right? Length when this is the input, will evaluate to 1 plus, and then the recursive call to the rest of the list plus 1. And this already is length defined with these two cases. So now we say length, and then colon something, colon something, colon something. So cons, and then an empty list, so that we get a cell, a list out of it. This doesn't work because length colon x axis. Yeah, here I was wrong here. That was like that. This is the pattern, and this is the what it evaluates to. Yeah. Okay, so can I do this? Evaluate again, and then yeah, there you go. Now I have it 2 times because I have this 2 times in the evaluation in the atom space. This length. That is yeah, I will figure that out soon. I suppose I will figure that out. Why? Because if I evaluate this here again, and by the way, I get these. The reason why the output looks like this is because this is the outcome of a prompt. Like this is the prompt character in the default meta wrapper here. Yeah, so this is kind of it's kind of it's kind of cute, but it also kind of doesn't say anything or whatever. So I'm gonna go into my meta mode, And I'm gonna say when I evaluate it, and when I evaluate this output, um, I'm gonna say if equal the output to this character, I'm gonna just say okay maybe or something like that, or do something cute. I'm not sure. Just isn't this this is like this is the little wizard fish. This is the small wizard in my vocabulary. Vocabulary. The small wizard, the small happy wizard. Okay, I'm gonna leave the small wizard there. When I evaluate now, sort of an empty expression. Oh, it's this as this. That was I was wrong. I'm gonna quickly say. I'm gonna quickly define this here. Okay, this is a little bit of emacs lisp here. In the middle, there's a space. Okay. So maybe like this. Okay, now it becomes this wizard. Yeah, I leave it with this wizard. I like that it makes this closure keyword makes it red, makes it pink on my emacs. So I think that's cute. Whatever, I leave it like this. It's kind of okay. So whenever you see this, it just means okay. Kind of, it means that I have evaluated this without any output. Kind of, I guess it's evaluated without output. Yeah. And the opposite is that you have output, then you get this vector of outputs. I think you always get this this tuple, this vector of outputs. So that's how it looks at the moment. Just so you know what happens when you see it. So now I get I don't know how many outputs here. Yes, how many? I could quickly put it into a closure buffer, because why not? Why not have a closure buffer at the same time? 8. Okay, whatever. Oh, this doesn't really work so well. Yeah, it doesn't have this. Okay, yeah, it doesn't. Yeah, okay. I know why this doesn't count as expression. I'm not gonna fix this right now. Okay. So this would be a recursive length, not tail recursive, because we go into the recursive call and then we still have work to do. So it's not tail recursive. But yeah, it's kind of like the default functional way of defining something like length. The function has two cases which are mutually exclusive de facto and act as a conditional control structure. The base case returns 0 for an empty list. Recursion itself takes place inside the second equality, in which length is defined via itself on the deconstructed parameter. Yes, so here this is a deconstruction where we say if you see the pattern colon and then an element which we call x and then some stuff which you call xs, or and then another element which we call xs. So xs is deconstructed. Notice that we didn't define the recursive data structure list and used arbitrary atoms, colon, and this empty list character as data constructors. Length can be called on anything, e.g. length hello world, but this expression will simply not be reduced because there are no suitable equalities for it. Yeah, so here we define an equality for length, colon, stuff, but this pattern is not defined for something like hello world, so this would just say it will just evaluate to the expression length hello world and not be reduced further, kind of. But if I would have this colon here, That should. This is. What is this actually? An error. This is an error. Yeah, um because it goes into, because it doesn't go into this base case. Basically, like this would work again, and yeah, or well, yeah, this would also work. This would be 1, of course. Yeah, something like that. But wait, what is the error actually? What is the error? The error is, in this case there is no error, and in this case there is an error, and it says that length expects. So there's a plus that takes more than 2 arguments, because length. Because length of world. Because length of world reduces to length world, and then plus has 2 arguments or something like that, I suppose. This is when I say plus, a +1, and then some stupid stuff like AB, then I get this error. Yeah. So that's the mechanism of this error, kind of, yeah. Coming from the fact that it doesn't, that you get something like this here at some point, because it doesn't reduce here, because this empty list symbol is never encountered, kind of. So back to the text. Length can be called on anything, but this expression will simply not be reduced because there are no suitable equalities for it. You can write your own version of length for other const nil instead of colon and empty list symbol. Yeah, that. Yes, you can change these. You can change colon to const and nil. Substitute this with nil, and you get the same output. If a function expects specific subsets of all possible expressions as input, types for corresponding atoms should be defined. That is for the type tutorial. Okay. Okay. Higher order functions. Continue in the text. Higher order functions is a powerful abstraction which naturally appears in Metta. Consider the following code. Okay, I'm gonna type what I say. Apply twice $f, so some kind of function, presumably $f, $x. Then it reduces to $f, $x. So it first applies f to x, and then it applies f to the result of that. Okay. Square, so it applies it twice. Square x, that is just a function. Let's pretend there's a function called square $x. That takes any x and then applies the multiplication x times x. Then let's say that there's a function called duplicate that takes an x and returns a new tuple of 2 times the x. Now we say that we evaluate apply twice square 2. Okay, so that will be 16. And you could type out what it does. So if we are the meta evaluator, we would see apply twice square. So without this, I suppose, we would see this form. Then we would say that we're gonna take this equality because we find this equality, it matches. So we're gonna use this equality to fill in the blanks. I think this is called beta reduction, basically. I'm not entirely sure. Oh, wait, oops. Oh, I already did it wrong. Oops. So F is... so you see this, and then you say that F is square and X is 2, and then you fill in the blanks, or fill in the variables. Okay, so it looks like this: square, square, and then here 2. If I evaluate this, I get 16. Yeah, and you could keep going here, of course. That would basically be that we do the same thing for here again, and it will expand to this. Yeah, that would also be 16, and this will expand to square. So actually this will be 4, and then it will expand to this. It will, yeah, like this. So 4 times 4. Um, that's sort of the process model. If unless I'm pretty sure this is more or less at least the surface level process model. Of course, it also does multiple it returns multiple evaluation outcomes as well. Okay, so this is all very sort of functional programming kind of simple concepts. Okay, so apply twice 1 2. Now I evaluate this. Nothing here because I need this exclamation mark. That yeah. So that one goes into this f. And this time f is this 1. But if you evaluate 1 2, right, you get this tuple 1 2. And then yeah, actually it's this. So it's just this. This is equivalent. These two. That is because the expression 1 2 doesn't reduce any further. Okay, that is all very straightforward stuff. Apply twice takes a function as its first parameter and applies it twice to its second parameter. In fact, it doesn't really care if it is a function or not. It simply constructs a corresponding expression for further evaluation. Passing functions into recursive functions is very convenient for processing various collections. All right. Yeah, so if we implement map, we say map with a function. The base case with an empty list would return the empty list. Okay. Then map with a function and with this ad hoc colon data syntax. That would be that this evaluates to a new list where we first apply f to the first element and then we apply recursively this to the rest of the input. Yeah, so I already have this function square defined. Then I'm gonna go with this function called twice x times 2, alright. Now we say map, and actually I'm gonna copy it at this point. Okay, so map square with this input list. That should, I mean, this is this sort of this beautiful basic functional programming structure here that we say run square on 1 and then on the rest of the list until there's no list anymore. Then it's just a empty list. So it returns a new list where this is squared, 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 and so forth. So, and we just have defined it ourselves. It's not too shabby, I think. Map twice, yeah. So that's basically with higher order functions, and this is sort of interesting, right? This is the place where in closure this would say a is not a function because it will go into f and then try to apply a to 1, like it basically goes here. This is a sub process of its thing. But the meta evaluator just says, I'm fine with this. I just don't reduce it further. I just give you the expression. So you get this default thing is that there are expressions somehow, and that already makes it quite self-reflective or meta kind of thing, that basically the basic thing is somehow these expressions. Now let's see where this goes. MEMP transforms all lists by applying a given function for a constructor to each element. There's a rich toolset for higher order functions and functional programming. They're covered in another tutorial. That would be interesting if this library is as good as the core, the closure one. That would be really interesting. But yeah, we can expect map reduce, iterate, fold, left fold, blah blah, and these things. This is called reductions in closure, I think. And then there's like the closure also has these transducers and so forth. But yeah, let's see. Okay, conditional statements. Okay, so you have an if primitive or something like that. Let us imagine we want to implement the factorial operation. If we want to use grounded arithmetics, we will not be able to use pattern matching to deconstruct a grounded number and distinguish the base in recursive cases. We can write fact of 0 is 1, but we cannot just write. What can we not just write? I'm just gonna believe them. This we cannot just write this fact of x is multiply x of fact minus x x minus 1. Fact with x minus 1. Why can we not just write this? Because x is anything somehow, or what? Why does this not work? What if I try to do that? What if I say fact of 0 is 1, and then fact of anything is this? Yeah, so these two things, and now fact of 5 doesn't. Oh no. This is an infinite. Oh. Why is this an infinite thing? What? I say fact of 5. Fact of 5 is 5 times fact of 5 minus 1, so 4. So it goes recursively into this x being 4. Then here it says 4 and 3 and so forth until 0, I would think. Oh, wait. But then it says, oh, maybe it says both. So because we can't distinguish 0 from anything else or something. This is, I think, the problem. We will not be able to use pattern matching to deconstruct a grounded number and distinguish the base in recursive cases. So yeah, that's the crux. I wonder if my REPL is now hung up or something. Yeah, I guess they don't. I wonder, is this broken now? Can I still evaluate things? No, I'm broken. I think I need to. It didn't make a now, yeah, it doesn't make a Stack Overflow error. Why not actually? This became 0. Huh. I guess it doesn't. It doesn't have. It doesn't. Maybe the evaluator is smart enough that it doesn't have Stack Overflow errors. But it was an infinite loop because when x is 0, then I don't then I go into both of these at the same time. Because I have this non-deterministic execution, and basically all the branches are supposed to return. So there is one branch that does return something, but the other branch goes one deeper again, and then that becomes -1, and so we don't bottom up out at any edge case, at any base case. We just call fucked again with -1 and then -2 and so forth. So we need some kind of conditional. Suppose they're probably right that we need this. Okay, no, I'm gonna kill my REPL and I'm gonna run it again. Meta, inferior meta. There you go. So this is evaluating again. Okay, so don't do this. Don't do this. You cannot distinguish the base case. Okay, so instead you use the if function or the if higher order meta function or whatever, however that is called, because I don't think they call this a macro. Let's see. So factorial if oh man, I'm gonna flip this. If x is bigger than 0, they said, okay, whatever, I'm gonna slavishly do what they do. If x is bigger than 0, I needed to. Jesus. I'm a fan of only having this in one way. So I always know that it goes from small to large. That is for me a very powerful thing about looking at greater than kind of constructs, that the small one is on the left and then it gets larger on the right. This is just very regular. So that comes from Zach Talman, Elements of Closure, where he talks about just don't use this one, just only use this one. And since then, I'm using this, and it's I don't want to go back. It's much more regular. There's kind of one thing less to think about, except when you copy code. I guess somebody is $x1. Okay, so if x is bigger than 0, then it's the recursive call where we say x is times the rest kind of the computation. But else it's 1, so if it's 0 or less, it's just 1. So now we have true base case. Actually, I would flip this if it was me. I like the base case at the top. So as soon as x is smaller than 0. Oh, do I need to say? Oh, never mind. I'm just gonna keep it like this. Yeah, if it's bigger than 0, then no, it's the correct semantics. Yeah. Okay, so exclamation mark factorial 520. Okay, cool. I think factorial 5. What happens if I say 30 here? Yeah. Okay, that's an error. Yeah, and I think I know this error. I saw this already. This error is. So now I don't print the error anywhere. Yeah, except in the output here. Oh, it takes really long. Oh, it dies. Okay. So actually, I sort of have captured the error right now randomly. Oh no, I didn't. Okay, never mind. This would be, yeah. Okay, well, I don't handle errors at the moment. So I'm gonna yeah, I would need something for errors. Yeah, that's true. I'm gonna here for the moment capture the output in a variable, like this, and then I'm gonna produce the error again, just out of interest. So you get this really, really ugly Rust error here. Rust error, attempt to multiply with node overflow. With overflow. Attempted to multiply with overflow. Yeah. So because factorial of 30 is large enough, it's probably not an int 32, I suppose, anymore. So it overflows in Rust and then bubbles up as an error into our user land here. So that's, there you go. That's and it crashes the the Rust process at the moment. So they you see it's a little bit raw still, this language. Yeah, it's early thing. This thing is, what I'm using here is called Hyperon experimental. So they're working on it. Okay, continue in the text. This was factorial. Factorial $x will be reduced to this recursive for if this is true. If this is true, so then that's also this is probably some, this is a grounded, yeah, this is another grounded built-in Rust implemented thing, I suppose. This greater than thing. If we would go in Hyperon experimental, we would find these built-in ops or grounded Boolean thing, but that will probably show up at some point. It should be noted that if doesn't value all its arguments. Yes, so that if is some kind of macro kind of thing, right? It's not a function, because else it would evaluate both of these and then for example return one or something, but it doesn't evaluate them. It must be implemented in terms of something like macro in order to do some stuff and then decide what to evaluate. So instead of a function, this needs to be something that operates on the expressions, on the inputs as well. And they will mention here how it should be noted that if doesn't evaluate all its arguments, but then and else branches are evaluated only when needed. Factorial wouldn't work otherwise, although this might be more obvious from the following code, which will not execute the infinite loop. Yeah, because if this would execute both branches, it would be infinite, exactly because of the point that I had up here, that basically it would go into -1 and then keep going, I suppose. And here, this infinite loop, okay, so if I say loop is equal to loop, and that would be an infinite loop. Now let's evaluate if true success, else loop. Yeah, okay, so this makes it obvious. This Turing machine would go into an infinite loop if we would ever evaluate a loop, but we don't evaluate a loop because it says true success, because the if doesn't actually evaluate its arguments. It actually does not evaluate one of those. It only evaluates one of those, not the other, depending on the predicate. The predicate, the consequence, and the alternative. It only evaluates if the predicate is true, then it evaluates the consequence, else it evaluates the alternative. Application of if looks like an ordinary function application, and if is indeed implemented in pure meta as a function. How this is done is discussed in another tutorial. Yep. this must be this higher this meta programming functionality basically. Another conditional, like the same thing that would be a macro in Clojure or Lisp. Another conditional statement in Meta is case, which pattern matches the given atom against a number of patterns sequentially in a mutually exclusive way. A different version of the factorial operation can be implemented. Okay, let's type this out, I guess. So I say factorial $x, and now instead of an if statement, I say case $x with an extra parens. If it's null, then say 0, and I guess that is a special. This is basically a special syntax for the case $x, and then this is basically the other branch of the function where it goes into the recursive. And now I have defined factorial 2 times, so I should get 2. Oh, I have defined it way more often or something. I don't know why I get. Why do I get it this amount of times now? This I don't know. This I don't know yet. But I think I get the feeling that at some point I will know. I got this. Yeah, I got it 64 times now, and that is I got 64 outputs, 64 branches where factorial was returned. How that came about. Or maybe it has to do with the number 5. If I have 1 here, I get it 4 times now. And 0 would be 2. Yeah, okay. And then it grows from there, I suppose. All right. Yeah, okay. Let's see. Thus, their usage is somewhat different. For example, if the usage between if and case is different. For example, if one wants to zip 2 lists, it is convenient to distinguish 2 cases when both lists are empty and both lists are not empty. But when 2 lists are of different lengths, there will be a situation when neither of these cases will be applicable and the expression will not be reduced. Yes, let's work through this example, I suppose. Okay, so say equals zip empty list is nothing. Okay, that makes sense. Then say zip with ::x and ::xs, x xs, console kind of thing, and a second input that is a list y with the rest ys, then return a new list where the first element is the pair of the first elements of the 2 input lists, and the rest is the recursive call xs and ys. Okay, this looks reasonable to me at first glance. If I evaluate zip with a, then b empty list, and then I do this a second time with some other kind of list 1 2. That works. Yeah, I get a 1 b 2 out of that. That's what we wanted. Now a b 1. Okay, that's now I have 2 different lengths here, and this will just not work. Wait, this should do something wrong. Yeah, it basically, okay, so the first call kind of works, and then I go into a case where neither of these 2 cases matches, and I have the problem. And I just don't reduce this version, so I end up saying zip with some list and then an empty list because neither of these was matching, so I end up here. with this half reduced thing. This is, of course, that's not correct behavior of the zip function, I would say. So in the text, the non-matchable part remains unreduced. Of course, adding two equalities for these two cases could be used, and you can try add them. Yeah. So I can as a as a as exercise. This would have fixed it basically. If I have the case where there's a list and nothing. Actually, what do you do with zip when there's nothing? Then it's just nothing, right? And then that depends on your semantic of zip. But yeah, I'm gonna do it like this so that the moment one list is finished, the zip just returns, so that the rest of the other list is cut away. So this semantic I get by defining these two equalities here. So now I have basically defined these intermediate cases, or these mixed cases, these mixed input cases, and now the with mixed cases defined, I get a list with one, where one was zipped and then it finished. Yeah, and the B was dropped. So there was the semantic I went with. Yeah, okay, that would work, but now they say something where we use case instead of this construct. So let's see. And it would be more preferable way in some cases. Some cases this is better than some case statement. However, using case here could be more convenient. Okay, let's type the same thing with case. And I'm gonna say zip with case here to not clutter the evaluator. Okay, list $1, list 2. Alright, okay, so this is kind of a function with these two arguments, and now we say a case. So this is kind of like an ad hoc pattern matching kind of thing, where basically we use, I'm guessing we use the same mechanic that would also look for these equalities, but now we kind of say it ad hoc, I suppose, more or less. Okay, so now case takes the cases in parentheses. Then I say the case where this is empty and this is empty, right? In that case, I'm gonna return the empty list. Yeah. So this is the first case. This is the empty list case. So here are the cases, and then empty lists, two empty lists, two empty lists. Returns the empty list. Okay. I think like that. I think that it works like that. Am I correct here? One sec. Can I quickly try out interactively a case, and then if I say something like this, then I say food, and I evaluate. That becomes nothing. Wait, that's not how case works, I think. One sec. Is there one too many? No, I don't think so. That's an error. Okay, cool. Invalid arguments, yeah, because there needs to be a list here. I'm surprised this didn't become foo. Let me go one simpler, 0. And now I say 0 becomes foo. Does this become foo? No, I'm still. Do I need one more paren? I needed one more paren because. So this is a list of cases, and each case is a paren. Um, these are the little experiments you need to do in order to get the syntax straight for a language like this. Yeah, so I needed one more here. Um, so it's that I have the list of cases, and each case is a list. So I need one more here. And yes, like this. Yeah, it's of course a little bit crazy, but it's just as crazy when you look at this here. But yeah, when you get it, it's not such a big deal. Also, you have these structural editing, emacs, movement things, or if your favorite editor. So you kind of you get a hold on it. So this would be case one, right? And I move around on case one. So this is case one, and then case two. Um, What? That is destructure the list. Okay, so case two is a pair of two things, and the first thing is the list x, where we destructure x, xs, and the second thing is the list where we say destructure y, y. Yeah, so this is the default case that we had already anyway, and the return value of this is a new list with the pair x, y, and then the recursive call is zip xs and $ys. That why does this already work? Oh, this returns error. So they make error. So okay, else error. I see. So they basically say it's undefined. And this $else is also special, or this is a catch-all variable now. All right. Error, and error is of course an ad hoc symbol as well. All right. Yeah, and then so this is case number two, and case number three, mixed. This means that one list ran out, so to say. One list ran out. One list was they weren't the same length. You can make an early exit as well by checking the length of these. But yeah, so okay now. Oh wait, I made a mistake here. Zip with case like this. So zip with case. Yeah, make this list A, B, nothing as the first list. Make this 1, 2, 1, 2, and then evaluate it. And yeah, I get it. I get it multiple times because I still need to figure out how to ask it for a single one. But yeah, bottom line is that this is the outcome. That is A1B2 list. Okay, so that worked, and then we can test what happens with basically invalid input, or what do we call invalid input now? Error. Then you get this error. We ran out of the second list, so we put error here. That was the case where one of them ran out, and then we say error. So basically we are here. We say zip with case, and then y was ran out, so it became error. So it became the pair. It became the pair, and then this symbol error. And I have it multiple times because I have some other sip with case. So I have two definitions of sip with case, so I'm sorry about that. The only way I know to fix this right now is to restart my meta evaluator, but I'm not gonna do that at the moment. Maybe I'll do it, but not now. Okay, free variables and non-determinism. Let's go. Continue in the text. Free variables and non-determinism again, recursively. Whoa. Let's go. That will be whoa. Yeah. No. Now we start talking. I think relational programming. Now it gets exciting. A piece of logic. We have already encountered if, which reduces to different expressions depending on whether its first argument is true or false. They are returned by such grounded operations as less than or equal. There's also such common logical operations as and or not. So to combine these Boolean things, you get this Boolean algebra, I suppose this is called. If true is true, if true, that is true, and if true and false is false. Okay, works like that. Default behavior that you would expect, I guess. See the standard lib tutorial for more information. All right. Let's go. I'm gonna give this a name. I'm so excited. I'm gonna give it a name. Here, like that, and I'm gonna make it even more visible. All right, a piece of logic. Okay. Things start to get interesting when we pass free variables into logical expressions. Whoa. Let's consider the following program. Okay, I'm gonna type what they say. Some facts as very basic equality. As very basic equalities. Okay, so there's an equality, says Croaks, Fritz. This is a German name, I think, or this is a name that sounds very German to me. Equal croaks, Fritz, true. Okay, say that Fritz is croaking, I guess. Then eats with underscores now. Okay, eats flies. Maybe this is a prologue thing because no, it's very prologue-y. I don't know. Eats flies, Fritz. Okay, Fritz also eats flies. Okay, then equal, say, this is basically our knowledge database right now, right? Say that Sam is croaking. Okay. Say Sam is croaking. But Sam is not eating flies. Okay. Eats flies. Sam falls. Okay. So we start seeing that you can probably ask for everybody that eats flies or something, everybody that croaks and blah blah blah, things like this. If something croaks, okay, I'm gonna type what they say because I'm so excited. If something croaks and eats flies, it is a frog. All right. And note that if either croaks $x or eats flies $x is false, frog $x is also false, right? It needs to say and. Yeah, it needs to say and. Okay, so now we say frog, and it looks a little bit like a function, but it's this equality thing. And now we use the built-in grounded symbol and we say it croaks, it, like this x, croaks and eats flies, x. That also needs to return true somehow, evaluate to true. Okay, so this is an equality called frog. So now, one sec. I'm just gonna depart from what they do, whatever. Frog right frog of foo is an arrow actually. And Croaks expects 2 Boolean arguments. Oh, okay. That's an error. That's just an error. Alright. That's an error. Fair enough. Because I didn't handle that. Croaks through. Croaks through is not a Boolean. It's just this expression, croaks through. And that was throwing an error when it came to the end here. That's fair enough. But yeah, frog. Of course, now we basically have a frog. That is Fritz. That is true, yeah. And frog Sam would be false. Yeah, so that's turned out to work like that. Okay, so what do they do in the text? They say evaluate if frog x what? I'm surprised that you can just basically type on the top level an if, and it basically is useful. This is also very interesting for me here right now. That basically that I understood that equal is useful on the top level, but now we say if on the top level as well. So you say if, and then then this pattern frog x. If anything is a frog, then so if is basically, this is basically an equality as well. Oh, what? I think is frog, what the hell? Okay, let's see where this going. Is not frog, alright. Okay, so I can just evaluate this now. Oh my god. Fritz is frog. What the hell? Oh wait, dollar, it also needs a dollar here. What the hell? Wait one sec, this already. Oh, yeah, okay. I see. This is basically the same thing that was crazy in the first tutorial with the brother thing. The fact that you can just say to the evaluator frog x, and you get something out of that. Yeah. So this evaluates a true and false because we have two entities that that return something meaningful for frog, I suppose, in the database. This is this is kind of fascinating. Yeah. The fact that this basically is already querying the database and basically puts in the variables for Fritz and Sam, and you get this out. Yeah, like the level of abstraction is very high because we went from the database to a relationship. Now I get it twice, I suppose. Yeah. Get it twice because I've frog twice in the database, and then to a query, sort of with things filled in. Yeah, this is not something that you're used to if you're not used to relational programming. Then this is surprising. Yeah. Okay, so green x is true if frog x is true. Otherwise, it is not calculated. Okay. Green dollar x. So green anything. Green anything is if frog anything. Then it's true as empty. This is, I guess, an ad hoc symbol that we use. Or is this special, this empty thing? Maybe they say this. So this is this green thing. Yeah, and then it's the same thing now. I can say give this to the evaluator green $x. So it will look for everything in the atom space where green evaluates to something. Actually, I'm not 100%. Like, if how does basically if know that like why is it not the case that there's some random stuff like if a b is this an error? Nah, so this just evaluates to the expression if a b foo bar. Okay. It's only when this returns a boolean that it reduces further to foo. This is somehow the trick with this whole thing, I guess. Now, okay, all right. This is something to get used to. Okay, if green anything, I guess everything that returns booleans for green. So X is kind of anything, but then it becomes frog. Oh, how much work is this empty doing? Yeah. If I say green 2 and instead of saying empty, I say foo, is doing the same thing, I wonder. I'm not sure. It kind of depends if empty is something special or not. If, and then you say X is green. I don't know why capital case here now is green with capital case. This is strange for me. Okay, and then $x is not green. I keep deleting it. That says, interesting. If foo Sam is green, that's interesting. Get like a bunch of outcome. If foo Sam, because Sam is not green. If foo Sam is green, Sam is not green. Fritz is green. If foo Sam is green, Sam is not green. Fritz is green. All right. Fascinating. Okay, but yeah, green. If I use if I use this empty thing, I think my outcome will be different. That is green. No, it's the same thing, but using the green equality. Yeah, then I get the more sensible thing. I get it twice because I have defined something twice. I think. Yeah. I have defined frog twice. Yeah. If I define it 3 times, I get this 3 times here. Okay. It just says Fritz is green. Why does it not say the other guy is not green? The hell? Green X is true if frog X is true. Otherwise, it is not calculated. Otherwise, green is not calculated. If frog true, else empty. Okay, this empty thing is something special. Pretty sure, because when I say foo, I get then I get that Fritz is green and Sam is not green. I get the output. Sam is not green, and then if foo Sam is green. Funny. And there would be a third version. That is, of course, this is boring because it says that green is a synonym to frog, but this kind of makes this little series here complete. Yeah, this would return something a little bit more sensible. Was like what? and then evaluate this, I think. Yeah, this would say Sam is not green, Fritz is green. Sam is not green, Fritz is green, Sam is not green, Fritz is green. Okay, so it would be true 3 times true. But it's a synonym to, or an alias to frog in that case, true false. So then saying true false and empty, these things are kind of these things are special for this logic. Okay. Yeah, this is very early for me to understand this stuff. So I get the notion that I can query the database, that I can say empty to sort of stop the calculation, but sort of like this is kind of bottom up calculation, kind of. Yeah, okay, interesting. Continue in the text. There are some facts about Fritz and Sam, and there's a general rule about frogs. Just asking whether frog X is true, we can infer that Fritz is a frog, where Sam is not a frog. Yeah, that's true. I can say frog foo, that is an error. Yeah, frog Fritz, that was true, and false was a frog. But you can also just say frog X. You can just say frog X and you get some true and false. Okay, this is not so yeah. This doesn't help so much. What helps more is if you you return. So yeah, I understand something. I think $X frog X, right? This already gives me a list of tuples. Sam false, Fritz true, Sam false, blah blah, and so forth. Yeah, something like that. Because I allocate X to be anything, and then one possible outcome of this calculation is that X was Sam, and then frog of this particular X is false, and then X can also be Fritz, and then frog of Fritz is true, and so forth. Frog is true. We can frig why Sam is not a frog. Detailed analysis of how this works is given in another tutorial. We can infer that Fritz is a frog, why Sam is not a frog. Alright. Green $X is defined in such a way that it is true when frog X is true. However, if frog X is false, it returns this special thing, list empty, okay, which is evaluated to an empty set of results, which is equivalent to not defining a function on the corresponding data. Aha! I see. Aha. Running the above code reveals that Fritz is green, but we cannot say whether Sam is green or not. We cannot say that Sam is green because green just says nothing. It's like saying that green is not defined at all or something like that, because we say empty. We pretend that green is not defined with Sam as input or something, or with whatever the other guy. Yeah. Yeah. Make the replacement in the above code with the naive version of green. Green is frog. Yeah, I basically already did this. This is the same as this green number 3 version here. This result is Sam is not green. Yeah, that's true. That's true. To appear, which shows that green frog is equivalent. It's not the same as logical implication, even with Boolean return values. It's not the same as logical implication. Sam is not green. Wait, it shows that the equality green X, frog X is not the same as logical implication, even with Boolean return values. I don't fully get what that means. It's not the same as a logical implication. Why? Because Sam is not green. But Sam is the guy that is not a frog. Although it is not precisely the same as equivalence. This was okay. So the fact that we get Sam is not green shows that this is not the same as logical implication. Okay, but I just don't know what that means. I understand that green 2, green 3, and green are all different. This is what I understand. Whether I basically make an alias for the frog thing, or I put something else there, or I put this empty there. Okay, let's just continue. You can also try to add equal flies toward into the facts. Okay, let's do that. Okay, I'm gonna say that somebody is also eating flies. So Toad eats flies. True. All right. Now I say green Toad. Error. Oops. This is an error. Green Toad can be evaluated only partially. Particular behavior is not fixed and might be different for different versions of Metta. So okay, they say the behavior is not fixed in that case, so probably makes sense that there would sometimes maybe also be an error. This is because it's for the same reason that frog foo is also an error. Because I ask for croaks and eats flies, and it just is not reduced. And then in the case in that case, this and operator's primitive operator or grounded operation basically sees some expression instead, but it throws an error unless in this implementation throws an error unless it sees two booleans. That is, and that's why green Toad is an error. So yes, it can be evaluated partially. Yeah, I wouldn't need to say that. Yeah, but sure. I mean, I already know that. If I also say croaks Toad true, then this would of course work again. That was not surprising, no. Okay. Continue in the text. Recursion with non-determinism. Okay. Let us generalize generation of random binary pairs to binary lists of a given length. Yes, that is when I have 0 and 1 and I generate a binary list of length 2, I get the Cartesian product of 0, 0, 0, 1, 1, 0, and 1, 1. And now I want to generalize this to any length n. Okay. All right. So random bit equal bin 0. This is fascinating to me. Yeah, you just say two things. Bin means two things. There's something joyful about this. I'm intrigued. Okay, then I say gen binary $n. Okay, this is basically a function kind of. If if n is bigger than 0, then I'm gonna return a new list where I make a random. Oh my god, this is cool. I make a random binary, and the rest is gen binary with one less number. So just a recursive call. Oh my god, this is really nice now. Okay, that is super cool. That is super cool. So that I can basically use the easy to think about simple recursive idea of generate binary and implement it recursively, add a random thing to the front, and then the rest is the list, right? Um, without thinking about without thinking about the combinations, without thinking about the Cartesian product, without thinking about um, without having any kind of loop. Um, yeah, this is seriously cool now. That basically now I get, oh, this takes a bit. I'm not sure where the bottleneck is there now, or this takes quite a bit. 6 is also already, whoa, shit. This is already a lot. Yeah, true. I guess this, yeah, combinatorial explosion. Okay, I'm just gonna say 2. Okay, so I get a list of results, and these are um, the four results um, that we were thinking about. That is 0, 1, 0, 0, 1, 1, and 1, 0. Yeah. Um, man. Yeah. Yeah. This is interesting. Yeah. Okay, 3. This would already like explode quite a bit. Yeah, but yeah, it's all these combinations: 0, 1, 0, 0, 1, 1, 0, 0, 0, blah blah, and so forth. Um, yeah, the fact that this line is doing all the work, I like. This is give me all the results of gen bin, and then add the result of bin, but the result of bin is two things at the same time, so that the results are being combinatorically exploded automatically. I don't know if that's the right term, but um, it will generate all the binary strings of length 3. So if I say gen bin 3, yeah. Similarly, functions to generate all the binary trees of a given depth, or all the strings up to a certain length, can be written. Try to write a function which will output the binary list of the same length as its input list. You don't need to calculate the length of the list. And to use if. You don't need to use if. What? Gen binary list with an empty list would be an empty list. Okay, I don't need to say if. Okay, so that if there's any input, then I'm gonna return a new list with a binary and then a recursive call gen binary list $xs. That's already it. Well, this was wrong. Gen bin. One sec, I'm gonna rename this because I cluttered the environment now. So okay, gen bin list 2 with $1 colon 5 colon 7 list. Okay, this should be the same. This should basically be this. So for each element in the list I return, but now the funny thing is I sort of blow it up. Like I did two branches, like 0 and 1. So it ends up returning 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, and whatever the rest, I don't know. Yeah, I think this works. Yeah. Okay, I did what they said. I'm happy. You can also make the binary trees of a given depth. Let's quickly do that as well. That would be kind of cool to be able to do that. Let's maybe go to the Wikipedia article of binary tree. Yeah, so you have nodes, and then every node has 2 edges. So you would write this. How do you write this? By saying that. What is sort of the default way of writing this down? This is already a binary tree, right? Value left subtree, right subtree. Okay. Yeah, maybe like this. Yeah, maybe let's take this sort of as template idea. So this is basically one subtree in the binary tree. Yeah, so basically I'm gonna substitute this with this bin. Yeah. So this is gonna say bin and then left subtree, right subtree, something like that. And then I'm gonna make an equality out of that. That's gonna say binary tree. With a number $n. Now if n is small or equal to 0, then it's gonna be this empty tree. Maybe that's just like that. And otherwise it's gonna be this. So that's gonna be a new list with the left and right subtree. So it's just out of aesthetics. This would make sense. Yeah, this makes sense. We bring up the Wikipedia article again. So value is 0, 1, right? 0, 1, 0, 1, 0, 1. Then let's quickly imagine, or let's quickly go through it. If binary tree of 0 is just nothing, I guess this makes kind of sense vicariously, right? The binary tree, or all binary trees of length 1, so I imagine that there's basically nothing but this part. Yeah, and then he points to empty. Yeah, this kind of makes sense. Yeah, kind of makes nice sense. Maybe I can I. One day I'm gonna be a master here, and I'm gonna quickly switch the color to something. Where's that color thing? The hell? I don't see it. Why do I not see the color switcher? Fuck. I'm pretty sure there's a way. This is pencil, circle. Okay, I'm learning here. Let me quickly figure this out. Key bindings. Color. Spacebar, color, toggle visibility. Right click, show the color wheel. I knew it was something simple. Okay, so do something like this, then show the color bar. Yeah, and then I have here these empty nodes to say that this is the this is the tree with two empty subtrees and one value. But because I return all possible subtrees, I actually say here I actually say 2 at the same time. So, but this is actually 1 and 0. So maybe I should have. I should have said. I should say this. I think makes it. Okay, I'm gonna one day I'm gonna figure it out. Oh my god, no. That was that is gonna be roughly something like that. It's gonna be roughly a list where the first one says 0 and then empty, and the second one says 1 and empty. So this is the binary, all binary subtrees of, all binary trees. With 2 values, and it's all of them with of depth 1. So that is what I get out of here actually. And when I say 2, then I expect the output to be in this case it should say here something like that. So this would be this roughly. Yeah, so it would say it would say 0. I guess I need to 0 and then 0. I guess it's too small now. Naja. Yeah, one day I'm gonna be a master. I need to quickly modify the text scale as well. Can I do it? Color. I guess I cut this out of the video then. So that would be that there's a 0 here and then a 0 here and a 0 here, and then there's here the empty subtrees again. I guess it needs to sort of go in this way. No, it needs to go only like this, I suppose. So this would be one possible one of depth 2, 0 0 0, and then all the other ones 1 0 0, and so forth. So that that should actually be returned here. So that would be 0, 0, 0. That would be that one, and then the rest. Okay, so what is the outcome here? This is already. I'm gonna put this into the closure buffer to see the data, because I have cprint. Feels bad. In order to I'm quickly renaming this to cons. And I try a third time. Also fix the recursive call here. Okay. Did I? Okay, now I quickly put this into my closure buffer. Delete this here. Okay, so there's 0. 0, 0, 0 is this one, yeah. I suppose this probably also makes sense that there's 8 outcomes. That's probably 3 to the power of 2. Yeah. Makes sense. So this is actually already as well the. Let me just clean this up, I guess. Something I still need to build up a little bit further. Doesn't handle the syntax yet. But yeah, this makes all the binary trees. What the hell? That's this is, yeah. It's the same thing we already saw with this other trick. That you can make a recursive function where suddenly you also get all the combinations of things. Yeah. Okay, this actually works. Recursion, this was the gen binary list. Continue in the text. Okay, and I also did this one. Yeah, that one that took a list as an input and basically returned a binary. It basically substituted a binary for all of them. Actually, just in closure, in closure, I would, in closure, I would be able to say map constantly, map constantly bin, and then the list. It would look like this in closure. I'm sure that basically we can make this in Meta as well, like this, when we use the higher order functions. Because here I define this in terms of return a new list, right? With a recursion here. Yeah. Okay, continue in the text.